Now let's change the engine that we're considering quite a bit. Instead of thinking of piston cylinder devices, let's think of turbine wheels and compressors. So now we've changed the engine so that each of the processes occur in a different unit. So compression occurs in a compressor, combustion occurs in a combustion chamber that's separate from the compressor area, and a turbine expands the hot gases. We're still going to use air, and so we'll have isentropic compression from state 1 to state 2, constant pressure heat addition, because the combustion chamber in the typical gas turbine engine is just an open area after the compressor before the turbine where fuel is sprayed in. And as long as the temperature is high enough, that fuel automatically just begins to burn. There's no need for a spark plug to continuously fire and start the burning process. So once you get it going, it just keeps going unless you have a flame out for some reason. But anyway, so that from 2 to 3 is basically just an open area where the fuel can burn. So there's no difference in the pressure between state 2 and state 3, even though the temperature of the air and fuel that come in goes up after the fuel is burned. That's not going to naturally increase the pressure on one side of the chamber and not on the other, right? I mean, the pressure is going to equilibrate throughout the chamber. So there's constant pressure heat addition from state 2 to state 3, and then through the turbine, state 3 to state 4 is isentropic expansion. Even though we're not talking about a piston doing the compression or the expansion, we can still talk about the compressor and turbine being isentropic. In other words, they are adiabatic, no heat transfer, and reversible. So ideally no friction, no fast compression or expansion of the gases. And so they can be isentropic. So each of these processes are still, the compression and turbine process at least, are still isentropic. And then, instead of what would happen in a real gas turbine engine where the exhaust from the turbine is simply spit out to the atmosphere, what we're going to do is take that air and run it through a heat exchanger representing the atmosphere cooling down the air before it comes back into the compressor. So we've replaced in the combustion chamber, we've replaced that with a heat exchanger where heat is simply added as the air flows through. And then instead of the atmosphere, we've got a heat exchanger where waste heat is extracted from the system. It becomes a closed loop system then. Now, because the turbine is dealing with a relatively high specific volume fluid, and the compressor is as well, both have large work interactions. In other words, the turbine produces a lot of work, but the compressor is going to consume a lot of work. Now, fortunately, the specific volume of the air in the turbine is higher than the specific volume of the air in the compressor. Therefore, there's a net work output. But there's another term we need to define called the back work ratio. And so you see the little diagram there off to the right that represents the total amount of work coming out of the turbine, and a significant portion of that work being sent back to the compressor just to keep the cycle going. So that's one thing to talk about, is the back work ratio. But there's another thing to talk about. Before we had a compression ratio in both the diesel and the Otto cycle, but now we've got what we'll call a pressure ratio. If you think about what's going on here, we already argued for the reason that state 2 and state 3 have the same pressure. But if in the real world what we're doing is pulling in air from the atmosphere and exhausting waste gases to the atmosphere, then the pressure at state 1 and state 4 are the same as well. So really there's a high pressure side of this engine and a low pressure side. The low pressure side is state 1 and 4 where the pressures are equal, and the high pressure side is state 2 and 3. Now we've made an assumption here, because in the real world there is pressure loss in the the combustion chamber, and there is a difference in the pressure coming into the compressor and the exhaust gases out of the turbine. The exhaust gases out of the turbine are going to be a higher pressure as they exhaust and go out to the atmosphere, and of course the compressor is trying to get air to flow in, and the only way to do that is for the atmosphere to push it in. So the pressure coming into the compressor is lower than the pressure coming out at the turbine, but we're going to neglect those because the pressure difference across the turbine and compressor from state 1 to state 2 or 3 to 4, those pressure changes are so large we can neglect the changes from 2 to 3 and 1 to 4. So we call the process, the heat addition and heat rejection process, 2 to 3 and 4 to 1, we call those constant pressure heat addition and heat rejection processes respectively. And then we can define what's called a pressure ratio, which is just the pressure at the the high side over the pressure at the low side, P2 over P1 for example. Of course that can also be written as P3 over P4, because P3 and P2 are the same thing, P1 and P4 are the same thing, at least for our idealized cycle here. The back work ratio we define as all the work produced by the compressor, all the work consumed by the compressor divided by the total work produced by the turbine. So in our arrow diagram, it looks like about half of the work goes back to the compressor, so our back work ratio would be 50%, which should make some sense to you. I just be careful, some students make the mistake of trying to take the net work as the work produced by the turbine, and of course that isn't the case. Now the cycle diagrams, again, you should find them in your book and you should mark them and write down equations as I show them to you, or at least highlight them. But you'll notice that we've switched them, right? We've got the PV diagram at the bottom and the TS diagram at the top. The TS diagram really doesn't look like it's changed much. It looks actually quite a bit like the diesel cycle, because we've got our isentropic compression from 1 to 2, 2 to 3 constant pressure heat addition, 3 to 4 isentropic expansion, and then 4 to 1 was a constant volume heat rejection process in both the Otto cycle and the diesel cycle. But in this Brayton cycle, the heat rejection process from 4 to 1 is a constant pressure process, because of course it occurs in the atmosphere in the real world in a heat exchanger in our idealized system. Now consider what's happened to the Brayton cycle on the PV diagram. 1 to 2 is isentropic compression, that matches the diesel cycle. 2 to 3, constant pressure heat addition, again matches the diesel cycle, as does 3 to 4, the isentropic expansion. What has changed now is 4 to 1. And so 4 to 1, the constant pressure heat rejection was a constant volume heat rejection in both the Otto cycle and the diesel cycle, and that's the big change. Notice we went from the compression and expansion process in the Otto cycle from being vertical lines on the PV diagram, in other words constant volume, to them being constant pressure in the diesel cycle, constant volume, and now constant pressure heat addition, constant pressure heat rejection in the Brayton cycle. So there is a logical progression in going from the Otto cycle to the diesel cycle to the Brayton cycle, and that's it. We're just changing one process each place. Notice that we're not really even making a distinction between compressor wheels and pistons. I mean, this is a pretty big, how should I say it, approximation or idealization. But fundamentally, what matters is the processes that make up the cycle thermodynamically, and that's what we're really trying to focus on here. Now, since we have open devices that have mass flowing through them, we need an energy balance that includes the flow energy of the working fluids. It's still air that's going through the system, but that air is flowing, so we've got to include the flow energy, and so that's why we've got enthalpy changes from the exit to inlet here, along with our net heat transfer and net work interaction. So it's unlike the energy balances we used for the Otto and diesel cycle in that those were closed system balances. This is an open system balance, and we can apply this equation to any of the 4 pieces of equipment, but there are only 2 where it's really useful. It's particularly useful to apply an isentropic equation to the compressor and to the turbine, and in this case we won't choose the same isentropic equation we chose so far. We'll choose the one that involves pressure instead of the one that involves volumes, because remember, we've got a pressure ratio now, and so it's convenient to talk in terms of pressures instead of specific volumes. So there's the isentropic equation for the compressor, and then we can write an energy balance for the heat addition process in the burn chamber, basically, in the heat exchanger there. And notice that it's just Qn equals delta H, because there's no work interaction during heat addition in that combustion chamber. So it's just a Cp delta T term. Here's our isentropic equation for the turbine, the expansion process. Ideally, again, it would be isentropic and adiabatic and reversible, therefore where we can use this equation to relate the temperatures across the turbine to the pressures across the turbine. And then finally, our waste heat rejection process, 4 to 1, can use an energy balance to quantify it, to relate the temperatures in states 1 and 4. So again, there's only a heat interaction. That's the only energy flow is heat in 4 to 1, and so it can be represented as the change in enthalpy across that heat exchanger, which we can approximate as a Cp delta T term.